called this Ferry Bridge Power Station cooling tower. They designed each cooling tower using the pressure distribution based on isolated cooling tower, no nearby cooling tower. But when they actually construct, they construct in this staggered format, okay, close to each other, and this produce the wind pressure about 2-3 times higher than what they use in the design, and leading to the failure. For tall buildings, the wind load can produce an effect called the resonance response. Okay, response become important for flexible and tall structure like tall buildings. This will show you some idea. It's a plot of wind force against time. You can see that the wind force is not static force because wind velocity is not static. Okay, wind velocity fluctuates with time, but it fluctuates slowly. All right. So you have wind force up, wind force down when you plot against time. Now, if the building is not so flexible, not so large, we call mid-rise building, with a rather high natural frequency, response will be mostly quasi-static. It looks like static response. That means when the load is high, response is high. When the load is low, response is low. Response will go increase or decrease in proportion to the load. All right. But when you have a high-rise building with low natural frequency, okay, which is typical for tall buildings with 30 story up, you have additional one. You can see this fluctuation, right? On top of quasi-static response, vibration, okay? Mostly in its fundamental natural frequency, okay? The structure will sway back and forth, oscillate around this quasi-static response. So you have additional resonance component. The methodology to handle this is called gas response factor analysis. Okay, and if you look at the American standard, Australian standard, Canadian standard, Japanese standard, they all use gas response factor procedure to handle this for the design of tall buildings. It's a case for Thailand. We have our own standard, and this is a latest version for Thailand. And we make our own standard by combining, using many existing standards as a model. Typically, we follow Canadian standard, but for low-rise, we adopt American standard. For tall buildings, crosswind vibration, we use Japanese standard, okay, and combined with the Australian standard. So it's a kind of mix of many things. Now, I'd like to move on to show you other issues. This is called dynamic of tall chimney stack observatory tower. Okay. Normally the chimney stacks have circular section. Okay. This is the most economic shape. But if you put a circular section body in a wind stream or water, this is the test in water tunnel. It creates a stream of water. You will see that on the water flow this way. You will see a kind of a periodic pattern of rotational flow created behind this body. Okay, we call vortex trail or vortex shedding. It's a periodic pattern. And this periodic pattern is observed not only in a small scale but also in large scale. This is a satellite image of a cloud vortex behind a small island. Okay, so either it's large size, like island size, or a small size, like this. You can create vortex shading, okay, in the wind stream. Now the vortex formation behind this will create the change in the pressure around the body. All right. The pressure change will vary with the time, but it will come back to its original form. It means a periodic change in the pressure pattern. For example, this is one time instant. It has a pressure in the front, pressure suction in the back. When you indicate all these force, you get one force vector. Okay, it means that at this time instant, the wind due force is pointing this way. In a short time instant later, the pressure change to this, and vector size reduce. And in the next time instant, it swings to this horizontal. And the time instant later, it swings to the other direction. Okay? So the force change is magnitude as well as the direction. All right? During this periodic change in vortex pattern. So suppose you have a swinging force vector up down. It will create kind of impact to the structure. It will break into, and give some details. It can break into two components: the force along the wind direction and force across the wind direction. The across wind direction, the component will be larger than along wind. In fact, if you look at the total force, along wind force will be higher. But the fluctuating part is small. The static part is large. Okay? This is fluctuating part, means the part that shapes the structure. Okay? So most of the time, for this type of structure, when you have the wind, it will cause a sway in perpendicular direction. Okay, I think it's better to see the real case so that you will understand. Okay, so this is the tower, okay, under the strong wind. Wind coming this way, but the tower sway in the perpendicular direction. Okay, let me show you. Can you hear the sound? Okay, this is real, no special effect. So, and you don't want to be on the top of that tower. Okay, but it's created by this type of mechanism we call the vortex resonance. If this force happen to have a frequency match with the structure, it will produce this large crosswind response. Yeah, this is a practical solution. Okay, used in designed by practical engineers, wrapping helical wire around the stack. The idea of this is to to make it shape the vortex at the different phase. Okay? So that it will not correlate. It's like you help pushing a car, but push not at the same time. Okay? You ask one to push at a different time, so it will not combine into a big force. This idea works very well in a small model in the lab. But when we try it in the actual prototype, I got a very conflicting report. So we are actually not sure that this approach will work, but it's widely used. Okay? This is another approach. If you have a very slender stack and you want to prevent the vibration or the wind effect, you have to have external skeleton. Or if you have space, you can put a guide rope. Okay? This is another approach. Looks like nothing, but on the top, we put kind of a Joule mass damper. It's a kind of a dynamic damper placed on top. From the ground, you cannot see them well. On the top, it just looks like a ring here. Okay? It's made from a steel ring, like this. It's in the factory, hanging by wire rope at 3 corners and attached with viscous damper. This ring is kind of pendulum. When the stack starts to oscillate, the ring will move more and will produce the opposite direction force to suppress the oscillation. So this is the kind we call this damper. Okay, when structure is starting to move, this will damp out the motion. Okay. You can see that the components are quite simple, and most of the components are constructed by local contractor, except the viscous damper have to purchase from Germany. Actually, we here designed the damper for it. And this one is another project, very tall steel stack in Rayong of Thailand. It's probably the tallest here in Thailand. And from analysis, it showed that the structure may oscillate in 2 modes by wind. The first mode is simple sway with the frequency of 0.8, 0.7 Hertz. Second mode is about 2. Okay? And the shape of vibration is different. But both of them can oscillate in wind. These are our analysis. It shows that for different wind speed, this is amplitude of oscillation. Okay? We conduct analysis for 3 values of damping because we are not exactly sure what is a damping value. I hope you all understand what is damping. Huh? What is the damping value the structure has? So because it was the time before the structure was built, so we have to guess. This is from the statistic. It's range between the low number to high number. Low is very low, high is not so high, about 1%. And it say that if the damping is low, we may end up with a problem. Oscillation will be too large. The movement may be 0.6 meter, 1 meter amplitude. If you create bending fatigue in the column, in the stack, you're leading to some damage if it's sustained. But if we add damper, if we reduce down to this, if you have a 2% damping, 3%, 4, 5, 2 is okay, 3, 4, 5 are better. Okay, but with and without, you see the big difference. Okay, with damper, it can guarantee that the amplitude will drop down to very low. So we then design damper to get about 4% or 5%. But if we achieve 2% is still good enough. Okay, that is the idea. This is for second mode. And without damper, if we put dampers, then it will drop down to the level that we don't have to worry. That is how we put the damper. This is for second mode. Okay, that's a steel ring, that's a wire rope, the viscous damper. We have this a team when we install this damper. And we have it, two of them, one for mode 2, the other one for mode 1. And they are designed by different parameters, which I don't want to go into detail. This is just an overview. Okay? But the size of the ring is small enough that you can carry by crane, put it on the top, and it's continue to work until today. I hope it will continue to work until the end of the service. And we can stop them as well by putting some locking device. Just lock, not preventing the damper to move between the damper, the ring, and the column. When we lock them, we can check the performance of the stack without damper. And then we remove the lock, allow them to move. We can check the performance with the damper. So by doing that, then we can see how damping change. When we lock damper, is decay very slowly. When we unlock the damper, the structure decay very fast. I mean, it dissipates energy very fast. I'm not sure you can feel this, but I think it's better to see how we work on it. Now that's me on the top. We try to shake the tower. We have a metronome. We say that, okay, move at this step. So we all move together, swing our body. After that we stop and see how it works. This is a vibration signal. Okay, we put the sensor on top of the tower. So while we swing our body, we can see how the structure moves. The people on the ground can see as well. Okay? It was fun, but a bit scary. Okay, then you can have this record. Okay? That's for the first mode. When we do a second mode, it looks like this. 2 Hz. Okay, very heavy. So it's a very good exercise for me. After that day, I cannot wake up. Okay, come back here. Now you have not only, actually most observatory towers have this kind of damper. This is a Sydney tower, okay, in Australia. They have a ring type dual mass damper on the top, 1 unit, and in the column another 1 unit, to prevent the first mode and second mode, similar to the tower I just showed. This is more interesting. It's a Yokohama Marine Tower in Japan. They adopt this type of damper. No mass spring, no viscous damper, just plain container and water. Okay, and it can work. It works if you put enough number like this. You have many of them. When the tower moves, the water slosh, okay, and produce a counteracting force. It can reduce the vibration down to around 30% of the original level. Okay, but this structure is very light, steel structure, very light, very flexible, located in Yokohama, which is a windy city of Japan. So it's vibrating like this all the time, up to the level that people cannot operate. They feel motion sickness all the time. So when we put this in, then it's better. But I still feel vibration. Okay. Now I move to another subject, long span bridge. This is a very well-known case. Okay, Tacoma narrow bridge. If you see Discovery Channel, you hear about this story. But let me show you. Maybe this is better. Okay, this is a real bridge, built in 1940. Now we know that suspension bridge is flexible, but we don't think it's this flexible. Okay? Yeah, that's twisting angle. It's produced by the resonance effect. And after it's repeatedly oscillate like that for 1 hour, it causes a fatigue failure of the suspended rope, leading to that failure. Okay. Now this is a well-known case. It's a case that makes us understand this kind of wind effect, the resonance effect called flutter. But that actually flutter happened to many bridges before this bridge, before this one. The picture of a suspension bridge fell in about 100 years before Tacoma. Okay, the drawing shows the same vibration pattern. So it must have already destroyed many bridges in the past, but we just know about it. And this day we can, we can make a small model of the bridge and test in a wind tunnel. It's a laboratory that simulates wind flow. And we can check whether this bridge will become like Tacoma, become unstable in the wind, or will be stable. Okay? It is possible to conduct this type of test to check the stability of the bridge girder. Alright? This is an example of wind tunnel. It's a wind tunnel that we make. It's developed by AIT and Thammasat University, our neighbor. We invest in making this facility. It is now the largest wind tunnel in here in Thailand. It's inside the tunnel. So a section of bridge is put here, okay, and hang by spring outside. So the bridge section is exposed directly to the wind coming from the fan. You can see on the back. And we have to make a model similar to the actual structure geometrically, but the model can be much smaller. We call scale down model. Okay, this is the case in Vietnam, and we check this one, the stability of the bridge in Vietnam. So by this test, we can tell that some section is bad in aerodynamic sense, like a Tacoma with a large two-plate girders on two sides. That is that one. Thrust looks better, but the deep thrust is stable. So if you have deep thrust, okay, that allow wind to flow through, okay, this will be the most stable section. This is an implementation of this idea in Japan, Akashi Kaikyo Bridge. Alright? They use upper deck for road, lower deck for high-speed train. So it's a good use of deep thrust. And the wind tunnel model, okay, big model in the big wind tunnel in Japan. It is a size we cannot produce here, and the model itself costs a lot. It's about 40 meters long, and red carpets because it's an opening ceremony. Normally we do not have red carpets and ribbons. No, just model. Of course, there are not just one solution. There are many other solutions. You can have, how to say, streamlined box girder. Okay, box chair, which have a very high torsional stiffness, as well as very good aerodynamic performance. Okay, this is not so good. This is not that good, but the streamlined shape, like an airplane wing, aircraft wing, looks good. So this is the first application, Severn Bridge in UK. The box chair, streamlined. This is a cable stray bridge in Japan, Ashikawa. The actual structure shape is a rectangular shape, but they add two wings on two sides. This is not for structural reason. Okay, they just add this to make a good aerodynamic shape of the girder. Alright. This is a Ramanai cable stay bridge in Thailand. You can see the shape. It's a streamlined section. During the construction, and they're lifting up the index box. Another one, Rama 8 cable stay bridge in Bangkok. If you take a boat tour tonight, you see this one. I'm not sure there's a tour in the plan, but the structure looks like this. The structure is having two big girder on two sides and precast concrete deck in between. Okay, it's very efficient structure, but looks very ugly. And then they put the fiber reinforced plastic to wrap around this. We call it bridge enclosure system. So after they put the fiber reinforced plastic, it looks clean. And it's in the box shape. Alright? And make the girder become aerodynamically stable. It's a multi-purpose. It looks good. The box itself is a closing cell, and we can take out the water vapor because using a dehumidifier. Okay, take out the water vapor from the air, so we can extend the life of the steel member. Okay, reduce the rate of corrosion, and it's used to improve aerodynamic stability. Okay, the wind tunnel test is not only good for checking the dynamic stability of the long span bridge. You can do this for wind sensitive structure like billboard. Okay, a large billboard, 40 meter high. When it put in wind tunnel, it's become this small. Okay, we can scale it down, and we put on top of sensor. This is a force sensor at the base. which allow us to measure the force in the wind direction, vertical, lateral, moment, overturning moment, twisting moment, so on. Okay? This kind of technique will allow us to see the loading on the structure. So we can actually know at what condition it will produce very strong torsional effect.